Any questions before I start? Nothing? All right. Well, let me start off by saying that the next thing we're going to do in this chapter, there's really two things we're going to do. We did rectangular, metal, or conducting waveguides. The second thing are going to be dielectric waveguides. There's two types. They're either something that's rectangular, they're called slab waveguides, or they're fiber optic guides. Now, in both cases, well, actually in the second case of fiber optic, the way to really do that for the entirety is something where you do separation of variables. You do the del squared of E plus omega squared times mu epsilon E equals 0. You separate that in cylindrical coordinates because it's a cylindrical thing, and then solve for the boundary conditions. The problem is, in Dr. Wentworth's book, he does not go through that at all, and it requires Bessel functions. Have you all had Bessel functions? You had? All right, Bessel functions, I'm trying to give you a little perspective about this. Okay. Sines and cosines are really, we call them trig functions, but they're solutions of differential equations. If you take the second derivative of y with respect to x squared plus a times y equals 0, the solution to that is either a sine of square root of a times x or a cosine of square root of a times x. In other words, they're sines and cosines. That's what I'm getting at. Or e to the plus or minus j square root n. If you're solving the del squared operation and you have cylindrical coordinates, and I'm not going to get into this, then the solutions are called Bessel functions. Right? And a Bessel function is nothing more than the solution of a differential equation that governs the behavior of electromagnetic phenomena in a circular waveguide. Now, the problem is this book and our class does not include the topics of Bessel functions. So I'm going to go the way he did. I may, though, and I mean, if you want it, I will go through this Bessel function solutions because it's good to know, but you don't have to know it for this course. And I wish you did, because I think you would get more out of it if you had, you know how we do wave equation? We started with the del squared operations. We started with Maxwell's, and we got down to the actual solution. And it was the exact solution for the assumptions we made. But all the things we did were in planar cases. When we were inside rectangular waveguides, we solved them, but we did it for planar. You know, we just had rectangular guides, and we had sines or cosine variation. Well, you can't do cylinder guides, either conducting or non-conducting, without Bessel functions. And so that's the reason I'm omitting the nitty-gritty. Dr. Wentworth's book does this in terms of what's called a bounce diagram, where he talks about ray tracing. It's not exact. And it doesn't answer a very fundamental question about the lowest order mode. But anyway, let me start on this. And in your book, if you have your book, I'll try to be as clear as I can about this. And I'll tell you, this is not a very satisfying discussion, because it leaves you with, well, it leaves you looking at the lowest order mode and wondering how in the world did he get that out of what he did. And the truth is, I don't know. He just says it can be shown. Whenever I see it can be shown, and then the answer means you probably don't know how to get there, but here's the answer. The way you get there is solving Maxwell's equations exactly. And for this one, it's ray tracing more than anything. So this is the dielectric waveguide, and this is on page 401. I'm going to try to do this in a way. I'm going to cut to the chase, because a lot of this stuff is on page 401, and it's the dielectric waveguide. but put down it's rectangular. All right, so when you have a dielectric waveguide, there's only one dimension really of importance. Usually it's like this. They're going to have a very thin piece of metal. They're going to have something that is going to be quartz, something like that. It's going to have a constant width, and it'll be big. The width of this thing will be immense. All right, and then it'll have a thickness A. Now, A is much, much, much less than W. And here's what happens. It's transparent, all right? But it is a dielectric, so it has very low loss. What happens is the wave, just like the rectangular guide, bounces up and down between the plates and flies down there. But because it's a dielectric guide, there is no boundary condition that the electric field tangent to these regions. You could say this thing's made of quartz or something like that. And then the surrounding is air, the surrounding material is air. There's nothing that says the electric field has to go to zero there. Y'all follow me on this? Now, we use the tangent electric field equal to zero to get the boundary conditions and then solve for the allowable solutions for rectangular guides. Y'all remember that, right? We did that. Here, you don't have that. The way you have to solve it, and I want to try to explain this, inside the guide, the sines and cosine variation in the horizontal and vertical component will be the same, as well as the e to the plus or minus j beta z times z in the propagation term will be the same. But out here, there will also be an electric and magnetic field possible. Just bear with me, guys. So what they do is match boundary conditions, which becomes what are called transcendental solutions. Solutions where you don't have an empirical form for the actual solution. It's a little more complicated. So outside the guide, you match boundary conditions. Then what they do, when they do this, they set the reflection coefficients equal to 1, or they say there's no transmitted electromagnetic energy. Just bear with me on this one. At the critical angle or better, and everything stays confined. They go through the whole 9 yards, and I'm going to get there on this one. I can do this if you want me to. And they come out with a couple of things that are of importance. Now, I want to do this to be fair about the bounce diagram. Here's what Wimmer's book does, and he doesn't go into a lot of detail. We're going to take a look at just the cross section of the guide, how this thing's bouncing. So if we take a look at this, we got something thickness A. Think about cutting this right down the middle like this. And we're just going to look at a bounce diagram in that plane. So we have an electromagnetic field that comes up. I mean, it's propagated. We don't know if it's TE or TM. It could be either. Comes, hits here, bounces down here, then bounces, and this is in the book on page, I think, 400. He shows this. I'm not used to doing it this way, but you'll have to appreciate what he's doing. So he says if this is A, we're going to start adding some complexity. This material can have a given permittivity, or an index of refraction. Just call it N S for slab. And there's a given thickness here, A. So if this is the angle theta there, y'all with me on this? It's ricocheting down there. And the standard way to do this, if you're not going to solve Maxwell's equations, is this. You put in what is called a phase front right there. You draw a line that's perpendicular to this right here, so it's bouncing. And you got to say that the phase of this wave, in order for it to work and have constructive interference, if it's a phase front, a wave moving this way, then when this thing reflects, hits here, and comes back to this point, they'll be in phase, or it'll experience a 2 pi radian shift. Y'all follow me? If it was less than that, it's going to be destructive interference. It won't be at 100% adding, all right? And if it's exactly 180 degrees out of phase, then it completely destroys it, all right? But the only way you get any kind of coherent reflection is if the phase difference between here and here is about 2 pi, or n 2 pi, where n's an integer. Does that make sense to everybody?
Mm-hmm.
You're going to have to just take my word for it. It does. Now, it doesn't matter if it's TE or if it's TM. It doesn't matter if the E field's poking out or the H field's poking out. Right? It really doesn't in this one. And I know there's going to be, it's called a continuum. It doesn't go to 0 there. So what we're doing is saying the phase front has to be additive. What that means is this. And please try to understand. I'm not trying to make this complicated. I'm just trying to give you more of an appreciation than complete hand waving, like you'd get if you had a science program on PBS or something. So this distance right here, from here to here, that would be equal to A divided by the cosine of theta. Just take a look at that for a second and convince yourself. Y'all follow me? If that is A here, then we know that, you know, adjacent over hypotenuse is the cosine, therefore A over cosine is this distance from here to here. Y'all with me on that? You may not like it, but you just hang in there. Now what I do is this. I go ahead and I say that that's theta. That would have to be theta 2 because it's the angle of reflection. And that makes this angle right here 2 theta. Convince yourself of that, right? Because it's ricocheting back and forth. You could draw perpendicular and say it's theta that way, theta that way. Y'all with me? Now, if you look at this, this would be a right triangle right there. If I'm talking about that. Y'all with me on that so far? So if we take the total distance from here to here, that would be A over cosine theta. Then we have to take the distance from here to here. All right, well, this is where it gets kind of interesting. We know that if that's 2 theta and I have the hypotenuse here, then I know that this 2 theta, I could say that this side right here divided into hypotenuse, and I'll just, in his book, he does this. He calls this A, I think, and this B, and this point C, I believe. You can check the way he has it drawn. I might have it upside down, but A, B, C, yeah, he's got roughly that if you look. All right, so if I want the distance B to C, right here, I'll just call it L B to C. I can say that L B to C right here over this distance, which is divided by L A to B, all right, that would be the cosine of 2 theta. And therefore, if I wanted L B to C, it's L A to B times cosine of 2 theta. Or A to B times cosine of 2 theta. And then what he's going to do, I know this is going to be the distance from here to this point, which has got to be 2 pi in terms of radians. Now, I can use a half angle formula. It's on the bottom of this page, I believe, but there's a standard one. Cosine squared of theta is equal to 1/2 plus 1/2 2 cosine of 2 theta. You all remember those type of things, right? So I can go ahead and say cosine of 2 theta right there is 2, right, times cosine of theta squared. Then I plug that in here. And remember, LAB right here is A over cosine of theta. I'm going to write right under here. I have A over cosine of theta plus, and then I have LAB, which which is A over cosine of theta, and then cosine of 2 theta right there is going to be 2 cosines squared. Yeah, -1. And when all is said and done, you end up with this being equal to, and he shows us in his book, a 2a cosine theta incidence. Or theta, just my theta. Let's see. So you go through it. That'll cancel the cosine, right? And that gives you 2a. Oh, actually, this is that right? Let me just see. So this is going to be 2. Multiply everything by 2. -1. Yeah, that's right. And he has it there. Now, that's the distance traveled from here to here. And if I multiply that by beta, so beta in the core, or beta in slab times 2a cosine of theta incidence right there has to be 2 pi m, where m is going to be an integer number. Now there's also 2 times the phase change that would be associated with the reflection coefficients right here and here. This is where it gets kind of a little hairy. So we know reflection coefficients could either be, we know we're going to have eta 2, eta 1 if we use the impedances, and then eta 2, eta 1. And if it is a t, if it's t, this is cosine of theta incidence, cosine of theta transmitted, cosine theta incidence, plus cosine theta transmitted. Now, I'm not going to mess with this too much. I'm just giving you some perspective. Well, that's one that would be for like TE. For TM, this angle would flip. This would be transmitted. That would be incident. But in any other case, this has a magnitude. The reflection coefficient has some magnitude, and it also has a phase angle, right? In general, it's complex. Well, that phase angle is the phase angle I put here, because you got to include the phase change at the reflected points. When all is said and done, it has to be 2 pi. That's what he says in his book. Try to appreciate this. So if you look in his book, and he does what I do, and he shows it for the TE and TM mode and how to get the phase angle. When he does the whole 9, he doesn't do a whole lot here. He gets something, and this equation right here will ultimately come down to a transcendental solution. Just means there's no closed form. You have to iterate on the actual mathematical form. And what he does is show you that on page 402, equation 791. You're not held responsible. He did this in terms of the actual index of refraction, not ADAS, and it doesn't matter what you use, but I just want to tell you this. Solving 791 can only be done with the computer. You iterate to the solution, and I don't worry about that. What he does is show you graphically, if you have TE versus TM modes, how you plot one side of the equation versus another. You're plotting both versus angle theta I. And where there's intersection, that's the allowable points where it can operate. You all see that? I'm not going to ask you to do this. Just please appreciate it. For the TM mode, he shows it on the bottom, or at the bottom of page 403. In either case, you're solving this iteratively. But all this doesn't mean much to you. it doesn't. So what? We know the frequencies it's going to propagate. It doesn't tell me what frequency I have to be over before I just get one mode. You all follow me on this? Remember with a rectangular waveguide, half wavelength on the base, right, conducting waveguide, that gave you the lowest frequency. You had to be over that frequency to have anything propagate. All right, well, with fiber optics, there is no frequency you have to be over. Y'all hear me on that? All right, the thing is, the TM modes are the ones that will propagate when you get low enough in frequency. This won't show you. I'm just telling you that. The only way you're going to see that is if I solve the whole 9 yards on that. Because he's doing a bounce diagram thing. It's not the way to do it. You solve Maxwell's equations, you equate boundary conditions. Then you'll see the actual allowable mode, but I'm not going to worry about that right now. Here's the one you circle and underline and stuff like this. On page 404, equation 7.95. It will show you the condition for only one mode to propagate. And who can tell me why only one mode is needed? Why do we want that? Why don't we want 2 modes or 3 modes? What do different modes tell you, really? Different angles of things ricocheting at, right? And that means what? Different velocities of propagation. Why don't you want 2 modes or 2 different velocities of propagation anyway? The signal will get garbled at the end when you try to reassemble it, right? Remember I told you when you propagate down a waveguide, and if you put a little antenna, all the modes will propagate. You're basically just, the power will, some of it will go to the 1.0 mode, some of it to the 2.0, some of it to the 1.1. If that frequency you're using is above the cutoff, I mean, is above those cutoff frequencies, they're all going to propagate. How the energy actually is or how the fields are set up in there and the proportion of the power energy in one versus the other mode, that's an entirely different subject, much more complicated. But when those things are propagating down, if there are different speeds when they assemble at the other end, you might say, when it's coming off, then there's not coherency. Then you get garbling, right? Then you may get the same power down there, but they're roughly the same power. But the thing is, it's got no communication abilities at all, right? That's why you want only one mode. So what he does there with his equation, remember, this is for a slab waveguide. You don't care how wide it is, as long as it's a lot wider than A. That's the only thing you care about. The slab waveguides are something, you know, if you ever have to work with making microelectronic circuits with fiber optic linkage like this, spend some time and go ahead and take a look in a physics book or an advanced book in electrical engineering and see how they actually get the allowable modes by mating boundary conditions. This is not the formal where you're going to see it, and there's lots of discussions about this, I'm certain. So anyway, yeah.
In that equation there, what is the end value?
M are just integer values, it's the mode number.
So it is like the...
Yeah, and the lowest order mode will be called the 0th mode. It means, and this is the odd thing, for the 0th mode, he shows that, I think he says this, there will always be a TM0 mode, all right? You see that at the very top of page 404, well, he doesn't even show an O. You know how normally it's like TM10, or TM11, something like that. Well, the reason he's not showing the second one is the second dimension is assumed infinite. Right? So those mode numbers have to do with how many half wavelengths are between the top and the bottom and cutoff. Here you have 0. In other words, it's called the oath mode. It's going to be something where basically, oh boy, I'm going to really get myself in there. Put a noose around my neck on this one, but basically it's not a half wavelength. The thing's a lower frequency than the cutoff mode of the of the TM1 mode, the TM2 mode, You're below that cutoff frequency, all right? But once you're below the cutoff frequency where this thing's a half wavelength thick, now you only have one mode propagating. And the way it propagates is kind of, you got to match boundary conditions, but now you got something much longer than a half wave, but only one mode will propagate, no matter what frequency, no matter how low in frequency.
The only dimension that will be given is the n dimension.
And dimension will give you, yeah, and that's really, what that is going to be the number of half wavelengths that you got. But anyway, the idea for the requirement, and the way he puts it in, to have only one mode, and that's what you want, is going to be, and he does it this way, he has A over lambda naught is less than 1/2, and he does this with intrinsic, or with, index of refraction. So it's n1 squared minus n2 squared. And this is assuming mu relative is equal to 1, and it's not lossy. This can also be rendered as A over lambda naught. Well, I didn't put the index XR. Here, N1 would be the index of refraction of the actual slab, the thing that's containing it, it's a thickness A. And N2 is outside. Usually that's air, so it's 1. This is typically 1. And therefore, it's just the square root of N1. Now, the reason I'm saying that, just follow me on this. So this has got to be A over lambda naught, has to be less than that. Well, what does that really say? Well, this is 1 over, if we talk about N2 having to do with air, then we got the square root. N1 would just be epsilon relative 1, right? Minus 1. Y'all with me on this? Right? Well, here, if you look at this, actually, this is absolutely fine. You can put lambda naught as C over F, A over C over F, less than 1 over the square root of epsilon relative, or just epsilon relative 1. And because the index of refractions are just square root of epsilon relative, so if we square them, we're going to get this, epsilon relative 1 minus 1. And then you can solve for the frequency. This is really where I'm going with this. If I multiply both sides by F and then both sides by this, I get A times square root of epsilon relative 1 minus 1 divided by C right there is equal to, hold on, I'm sorry, I got this backwards. What I should do is this. This really brings F up top, like so. So I have F equal to C over A, right, C over A, and then it's equal to times 1 over the square root of epsilon relative in media 1, or in the slab minus 1. Now, that's the frequency. The reason they do wavelength, the reason he's putting that there, here's the reason. See how the wavelength's inherent there? A over wavelength. A is the thickness, right? Well, almost everything, you guys see this is extremely thin. Almost everything that they talk about when they're using slab waveguides is hundreds or thousands of nanometers. That's 0.1 microns or 0.001 microns. That's extremely thin because it's optical. Optical light, like stuff you see out here, is what? 700 to 1400 nanometers, right? You guys, that's the light you can see, right? Laser lights and stuff are in that range. But we don't talk about frequency with light because it's 10 to the 17th, 10 to the 16th benefit. What we do is talk about wavelengths, and usually in nanometers, right? That's the way, you've had optics in physics, right? Y'all remember that when you're dealing with optics? Normally, you don't talk about frequency, you talk about wavelength. That's how come this ratio is so important. Because if I know this ratio, let's say epsilon relative, just for the heck of it, is 2. 1 over 2 minus 1 is 1, right? 1 over 1 is 1. It means if I've got a material, which is about silicon dioxide, the dielectric of silicon dioxide, it means the wavelength has to be the thickness. All right? Now think about that. Say it's 1400 nanometers. That's 0.14 microns. You know how thin that is? I mean, that's extremely thin if you think about it. Y'all know 10 to the minus 6 meters is not something lithography usually gets. You can do it, but that's my point. These are very small structures when you're talking about optically connected guides. They make them, don't get me wrong. And it depends on the frequency or the wavelength. If you're getting down to lower frequencies than that, when you get into the maybe 80, 90 gigahertz range, then it's getting thicker. But usually, you're talking about that and optics in very, very thin layers. You can read about it. Now, I'm sorry if I seem a little unhappy with the, I like to do Maxwell's equations from the beginning and get the final solution, but this is one of those times where it might be a little over, it might be a little too much for something at this level of course. A senior course or a graduate course would definitely dive into the Bessel functions and do the boundary conditions. Now I'm going to go into the cylindrical waveguide, and I'm going to do it the way he does with ray tracing, but I'm going to delve a little more into it, make sense of some stuff. And this actually, believe it or not, the ray tracing for the cylinder fiber optic guide actually makes a lot more sense and is easier to understand, even though it's not exact. And I say that reluctantly. So now we're going to talk about fiber optics. Fiber optics are constant cross-section cylinders. Here's what a fiber optic cable looks like. This is in your books, by the way. It's basically this. And then you have a cladding around it. There's going to be a fiber core. Usually it's just labeled as F, the fiber core. It's got a certain radius. And around it is a cladding. And then there's something that's all around there. It's called a jacket, and it's to keep critters away. So if I blow that up a little, your core has some radius A, then this is going to have a radius B, and then you got the jacket around here. That's what they look like. The core material is the one that has the highest index of refraction. And in his book, he shows you a picture of it. It's got a radius A. It's got some intrinsic or some refractive index N sub F. Here in the cladding, you have N sub C. This is the cladding right here. This is the core. And that's the jacket. They're always going to be circular. Now here's something that does happen. I'm just going to mention this to you. See, this is a discrete, it's called a step index fiber. The inner core has a fiber, an intrinsic, or excuse me, it has a index of refraction that's constant. This is made of the same material through here. Then it abruptly goes from that index of refraction to the next one. Think about like quartz going to maybe, this won't be it, but like some sort of a polycarbonate thing, something like that. right? It's going from one to the second. Actually, what they do is take glass and they dope it differently, I think, for most of this. DuPont and some of these Dow Corning, they do this. So you got a core and then a clouding with a different index of refraction. Always NF is greater, although there's a small difference, will always be bigger than the clouding. Now for this one, I'm going to go through the 9 yards of it and make sure you get it. And in that way, you won't forget this one bit of it. So, like we did in the rectangular waveguide, information, if you think about this core here, information is going to ricochet off the interface as it comes, all right? The wave is going to come in here, and it's going to go down the guide bouncing. So I'm going to take a look at just the fiber, the core material right here. I'm going to draw it like this because I want to try to be consistent with the book. This is the core, or core fiber. Usually it's just subscript F. Then here's the cladding. And the fiber core has an index of refraction NF. The cladding N sub C in Dr. Wentworth's book. So we're going to take a look at this. And I'm going to draw a line right down the center and split it. And I'm going to say that we're going to have white. Now the funny thing is TM or TE has no bearing on this one. We're going to say I'm going to have an electromagnetic wave flowing in there at a certain angle. And we'll call this, and he does it, this is theta A. I'll tell you the page number of this. This picture of fiber optic cable is on 407, or optical fiber in place. This is on page 410 if you have your book here. It'll help you to follow along. Just turn there. Y'all with me on this one? Okay. So the wave's coming in at this angle, theta A. Then it's going to come out at this angle, theta B. This isn't hard to see. It's drawn in the book, maybe a little bit. It keeps going, strikes there. That angle is going to be theta C. And then it ricochets. Now, like before, in order to get constructive interference for anything to propagate, you can have only one mode. You all follow? I mean, what they'll do is you can put a wavefront down there and say that it has to add. We're not going to do that this time. We're going to omit that. We're just going to go right for the money right here. Here's the way to do it. Wentworth doesn't do this in the prior one. If you take a look at this, I know if I want total reflection, then I have to be at the critical angle out here, right? So just follow me on this. Let me digress right here. We know one thing about Snell's law, that we know if we come in at a certain angle right here, theta incident, then, and this is theta transmitted, and this is region 1, and this is region 2. I can write beta in region 1 times the sine of the incident angle is beta in region 2 times sine of the transmitted angle. Do you all remember that from Snell's law? Well, beta is omega times square root of mu1 or mu epsilon, and ultimately with all the cancellations, you can prove that you get the index of refraction in region 1, assuming mu relative is equal to 1, and n1 is index of refraction, times sine of angle, the incident angle, is equal to beta 2 times sine of the transmit angle. You all with me? So here's where the proof, the entirety of the proof lies. We want this angle right here, the second angle, right there, to be 90 degrees. That means everything's transmitted or reflected back. Nothing's transmitted into the second median. Make sense? Okay, so having said that, that means, I'm going to come over here. When I look at this, I have, this would be N, or the index of refraction of the fiber times the sine, and that would be a theta c, right? Because I'm trying to be consistent with Dr. Wentworth's books, would be equal to, and now that's the cladding, the index of refraction of the cladding times sine of the cladding angle, but that, this, let me just put it, theta, and I'll put CLAD. Well, this is going to go to 90 degrees. What's the sine of 90? Sine of 90 is 1, right? So it goes to 1. And that means we're going to let clad go to 90 degrees. The sine of 90 goes to 1. So I have this is equal to the sine of theta c. Just take a look at that, convince yourself. This is not a difficult proof, but it's the afternoon, it's Friday, and I already see a guy. One pseudo-casualty. I understand how you.
I'm migraine, it's not.
It's all right, it's all right. You go ahead and take care of yourself. Y'all with me on this one? You ought to see sometimes at the 8 o'clock classes, especially if it's a football week. Oh my gosh, it is snoring and everything. All right, now I got that, but I also have one here, right? And we'll call, and we're to be consistent, he says out here we're going to have eta, we're going to have the index of refraction out here. It's usually 1 because air usually has an epsilon relative 1, but not always. So then, let me erase this. Have you ever been in a class where somebody was snoring? I think I've had a few. I used to take that as an insult. I don't anymore. If you're that tired that you need some sleep, I'm going to leave you alone. Just deal with it. But I got stories about that. I've had kids literally texting, and then they stick in the earbuds, and they'll get a call, and then they start talking. They forget. They think they're talking, and I mean they're having a really lively conversation about something. Everybody's listening. That's the best one. That doesn't happen that often. Okay, back to this region right here. Now I'm going to use Snell's law there. So I take eta naught, right, times the sine of the angle theta A is equal to, and now it's going to be times index of refraction of a fiber times sine of theta B. Y'all follow me on this? This is not hard to see, right? That's just Snell's law there. Okay, but here's the neat thing about this. Here, now just look at that. The sine of theta C, right here, sine of this angle. Well, sine is going to be the opposite, right, over the hypotenuse. Y'all with me on that? If we're talking about this angle, the opposite would be from here to here, the hypotenuse is here. Well, that's also the cosine of theta B, is it? So I could replace this as cosine of theta B is equal to NC over NF. Y'all agree with that? Right? Because it's a right triangle. And also, I can square both sides. I'm going to use this. This is not that hard to see. Oh. It's going to go at me again. If I take this right here, y'all agree with that? Just square both sides. Now cosine squared is 1 minus sine squared, isn't it? So now I say that this is 1 minus the sine squared of theta b is equal to NC over NF squared. He has this in the book. I'm after the sine theta b, okay? So what I do is take this to the other side, this to this side, and I end up with the sine squared of theta b here will be equal to 1 minus NC over NF squared. Make sense to everybody? Finally, I get sine of theta b is equal to the square root of 1 minus quantity NC over NF squared. And here I just got sine in terms of, with the assumption that that angle into the cladding is 90 degrees. In terms of just material parameters, NC and NF, this becomes the critical feature. All right? Take that and I stick it in here. Y'all see that? Now, you'll notice there's NF there, right? So when I multiply this by NF, I end up with NF squared minus NC squared. And I end up with square root of NF squared, right, minus NC squared. And if I divide that by N naught, lo and behold, I get the sine of the actual angle of incidence. Now, let me just tell you why I did all that. This is the critical feature. We assume that that angle, this is 90 degrees, right? Any angle for theta c that's larger than that will guarantee it's reflected inside because you're past the critical angle, all right? Now, what does that mean here? Well, it means that any angle less than theta a, all right, it will completely reflect inside and pass, all right? What's really saying is the light coming in there, if theta a, suppose we've solved for it, was 20 degrees, all right? Any light at less than 20 degrees incidence on this thing would pass without any kind of reflection. You always remember the old mode propagates in the slab? All right. Well, for this, when we get down, when we get this point downward, it doesn't matter if it's TE or TM. It's going to propagate. The light will propagate. You got me on that? Really doesn't matter. If I'm coming straight on, guarantee it's going to propagate. But this is important because when you're dealing with fiber optic stuff, alignment becomes a problem. So you got fiber optic guide here, right? And I'm going to feed it with a laser. Well, if this laser is not aligned perfectly, if that angle, the critical, suppose theta a is like 1 degree, then you're not going to get any kind of communication. And has anybody ever worked with any kind of diode? You have fiber optic stuff? Did you have alignment? Did they ever give you a lecture about the importance of alignment, or did you just have plug-in stuff? All right, well, that's the way to like prevent misalignment, but misalignment becomes a problem, especially when you have a fiber optic. Usually it's just an optical photodiode that catches it, but if you have something where light beam is going right in optical fiber and you have a whole bunch of pieces of fiber optic out here, and you've got light that's actually being sprayed on it. Oh boy, that's a bad word, but there are things that do this. You have to make sure that you're at an angle less than this angle. Now that's called the numerical aperture. Just right, yeah.
Wouldn't that mean that your optic cable has to be pretty straight though? Otherwise you might.
Well, the optic cable, well, yeah, there are limits, but fiber optic cable, real fiber optic cable, it's buried in the ground. This is what we're talking about. That's made of glass. It'll bend a little, But you can't just put a 90-degree bend there. There's a maximum radius of curvature, or there's a minimal radius of curvature. Radius of curvature simply means that if you think about a spool, the radius of that spool, all right, has a certain length to it, and that means the radius of curvature dictates how much change there is, the bend versus small angle deflection. I won't get into that, but when you're dealing with this stuff, real glass and stuff like this, the fiber itself will never vary that much, all right? If it's going to vary, then they're going to have some sort of a corner reflector or something that the light hits the mirror and it bounces off of. Anyway, that said, write this down. This is the numerical aperture is what we're talking about. Numerical aperture is usually designated as NA, and it is the sine of theta A. So they don't give you a theta A. Usually if you buy fiber, what they'll do is give you something that'll have a given numerical aperture. Now, I don't work with fiber. I've been around it, I just don't work with it. This is more material science / physics if you're doing optical experiments. Normally in electrical engineering, at least the stuff I've done in computer engineering, the only thing fiber optics are used for is to get information at point A and B, and that information is what we deal with, signal processing, something like that. And anything we're going to do, we're going to deal with more than that. I mean, I'd have to have a very good reason to delve into the physics. I just don't. That's Dow Corning, people like that, DuPont. I don't do it. But anyway, this numerical aperture is the critical thing. Now, this is all well and good when you have step index fiber. This has a certain material. The outside has a very different but absolute discrete and continuous material outside of it. There's a strong discontinuity. There is also something called graded index fiber. You should at least be exposed to that term. It means that right around this boundary, it doesn't go from just one or the other. It slowly changes from one to the other. That's called a graded index fiber, or GRIN. Graded index, or graded GRIN, graded index numerical aperture, graded index index of refraction. But you can read that in the book. Those are used for multi-mode fiber, and I don't want to spend, it's going to be fiber optic stuff where you've got two different frequencies of light propagating down. You're going to ask me, why do you need that? I don't know exactly. Usually it's because you're trying to get two communication channels down one, and you're trying to probably go on the cheaper fiber instead of running both cables. Have you dealt with graded index fiber, or is yours?
Dealt with multi-mode.
Now, I don't know which one's more expensive. I think graded index, huh?
Single mode's a lot more expensive.
Single mode fiber, so step index fibers? I didn't know that, but step index is very, very small core on step index fiber. Something else you need to know about fiber optics, unlike waveguides. Waveguides transmit continually at a certain frequency, and they'll modulate, well, not all the time, not with radio, but generally speaking, you get like FM modulation on the signal. So there's always a signal present. It's a common communication. With fiber optics, you don't. You send a packet of photons and then nothing. Packet of photons and nothing. So there's, you might say, if you froze time and look spatially, you'll see a whole bunch of photons here and then nothing, then a whole bunch of photons, all propagating at the speed of light down, well, roughly the speed of light down thing. Now, that's like ones and zeros. It's basically in the digital form that you want it. You don't have to decode the thing. So they go flying down, and that means you get little, you could think of regions of light propagating down. Think of, you know, Star Wars, or they're firing their things, and you see like a packet moving. Well, that's what happens at the speed of light, literally, on fiber optic cable, and they have photodetectors that detect this, and the pulses have to have a certain duration in order for the photodetector to detect them. And then it's basically detecting it, 1, not zero, or vice versa, 1, 0. So all the information is sent digitally. And have you had your digital communications course?
Okay.
You had Digicom probably, right? Digital circuits or digital circuits. But did you have digital communications yet? Did you have your comm class with your Tender Tugman? You've had?
I'm negative now.
All right, well, if you're going to see that digital is the way everything's sent because you eliminate noise. You reduce noise tremendously with digital communications. And you have, depending on the type of material you're using, if you're using fiber optic cable, the amount of information you can get per second is ridiculously high. That's the reason they want fiber optic cable. One last thing I'm going to tell you is, right now they're putting fiber optic cable all over the United States. In another 10 years, I'm almost guaranteeing you our phone system and everything, the old Bell telephone buried cable is going to be done away with. Most of any type of comm links will be done with fiber. Problem is they have to get eminent domain permission to dig up your front lawn or whatever property you own. And places like New York City are a nightmare because I'm just going to say this. I'm glad I don't have to be a city engineer in a place like that, because trying to get right of way to put something in, there's everything. There's subways, there's sewer lines, there's water lines, you pick something that's out there. If you start digging, God help you, like, I don't work there, but here in Alabama, at least where I live, they can dig up my front lawn. They have before. All they want, as long as they have a permit and stuff like this, and they get it. So what I'm going to do with fiber optics is get in optical stuff. I am not going to hold you responsible for anything more than the numerical aperture. All right, and the thickness for one mode. And here's the nice thing. I'll give you the formula for thickness of one mode. So you just have to know what it is, all right? Now, the reason I do this is because I felt very, very bad about not going through the in-depth physics. If we have time at the end of the course, I would love to go through the full wave equation. I won't have you responsible for that, but do the whole 9 yards, and that way at least you'll say, I know how to do this if I need it. When I was in school, this is the difference. In physics, no physics professor would ever not do the entirety of the development of the formulas. That would be completely anathema. That would be a sin of the greatest order. It would be like not solving the differential equations for a kinematics problem. All right, guys, you know what time it is? It's that time of the week for your favorite. It's what you